last problem in your homework asked, hey, compare bisection and false position method, and how fast do both of them get to the solution. And in particular, we said, well, false position came about in attempting to be faster than bisection method. And here there was a problem where actually it was the other way around. And that is typically, it is often that we have to actually look into an individual case and that there is no general rule, and this was an exception to general behavior of the method. But actually the reason, most of you did not explain why that happens properly, and the reason is sitting in your slides. So this would be the expected behavior of bisection versus false position in terms of the numerical error and how fast. So the method where the error drops down faster is a better method. So in this case, in this schematic, false position would be better. However, in this case, which is basically the function you were looking at, x to the 10 minus 1, the function itself, which is here in black, it is way different than its linearization. So if I start on 0, 1, or around 0, 1, right, then the linearization of the function, which is basically what false position does, it approximates the function with one of these blue lines. Okay? So now my approximation of the function is this blue line versus the function itself is the black line. Look how far apart those are. So it's not going to do a good job. Okay? It's simply because this linear function is nowhere near the function itself. Okay? And therefore, so if my next lower, so I had a bracket that was this, and now my next lower bracket is from here. Okay, so this is my XR for false position. Then this is going to be my new interval. Then after that, this, so I'm kind of really inching slowly towards the actual root. Whereas bisection would just never actually look at the function itself, just divide in half and keep halving, and in itself is therefore faster in this particular case than false position would be. So often when you're actually looking for explanation, try to, this geometrical reasoning, what is false position doing, is helping here, right? Because it's actually approximating the function with this line, right? And that line is simply doing a poor job in representing the function itself. And in this particular case, it's resulting in a slower, way slower convergence toward the solution. It still does it, just takes forever, okay, to the solution than bisection method itself that doesn't look at the values of the function at all. Okay. So sometimes plotting the function, sometimes actually peeking into the slides and walking through the material before solving the problem, and sometimes actually just plotting the function and looking at it and also understanding geometrically what does the method do helps. And I actually tend to poke little questions like this on the exam, like what is the, geometrically, can you plot me the next step of the root finding method? So you can expect actually something like this on the exam. All right. So right now, the only one last thing that I would like to point out, we have basically covered all of the methods. You know the mechanics of how to program, and have done so already for homework. Just one more comment on how to become more efficient. So one thing that I want you to leave you with is that we're just starting to program. And as you go along in any problem, you first do quick and dirty solution. First, literally test your programming environment as a bit of a calculator as you start thinking through how you solve the problem. And then you solve it, And often you look back and you're like, well, this was not the most optimal solution. Even when you solve it, you're like, if you're up against the deadline at homework, you just submit and say, okay, bye, see ya. But like technically, if you're gonna come back to that program and use it later, which you often do in your professional life later, they're gonna look at it and evaluate and say, okay, I can do this better. Or it turns out to be slow and say, okay, maybe I can improve this or that. So your first solution is typically just that. It's a solution, right? And after that, you improve. So here's one comment that I want to make in terms of making all of this programming a little more efficient. And that is noticing that all of these, so let's look at this is the code that I did last time for Newton's method, okay? So this is my iteration. And it's a standard Newton iteration. I initialize my parameters. I define the function and the derivative. We know that we need, for the next iteration, it's old iteration minus f of old iteration divided by derivative of f at that same old iteration. And that is my core iteration step, okay? And that is all programmed here. We went through it last time. Here's that main line. Now, one thing that I don't want to do is every time, if I now turn around and in your next homework, you're going to get Newton's method for some other function. Okay? And technically, all you need to change is the definition of the function and the derivative. Okay? But is there a way, so what you could do in that case is just go in this, copy this as a separate piece of code, the entire cell, and just change this, what I call FF and DFF here. Okay? And then if I asked you to do it again, then you would have to do it again. That doesn't seem to be the best way. Okay? So maybe we can actually define Newton method as a function for one. And not only as a function, but also a function where I can pass the function as an input parameter. So then I just do that. So that's actually what I've done. So I just took this cell and I motivate you to do this right now. So just copy this cell on Newton's method and create a new code. I've already done that, so I'm going to show you because I wanted to write in a little more comments for it. And it's actually posted for you if you just want to download it. But essentially, I defined a function, Newton method, and it's going to take something that I call func, func, and derivative, so function and derivative as input. And then I just proceed as I did before. So I initialize, and it's also going to take the starting point as also, because that's something that I often need to tweak as I go, because not all starting points will give me a solution. Okay? So that's an actual one to have as an input as well. And you could actually have maximum number of iterations and this epsilon as an input as well. That doesn't matter. That I leave up to you. Okay? But what I'm actually really doing here is like, okay, my function and the derivative will be both inputs, and I'm going to use them right here as I did before. Okay? So what I did is I copied that previous code. I removed x0 from the initialization and made it an input. And I also changed name of this FF and DFF as function and derivative. And just replaced them here, the key part. And don't forget to indent 4 times. Okay. And one more thing at the end, I also did a really little nicer printouts. I said, okay, root is x1, just this last iteration printed out, and how many iterations I got to go there. And I can actually return that x1 You can return whatever you'd like from this function. I'm just going to focus on x1. So how do I use this now? Okay. I need function and derivative as separate functions that are just with one parameter. So I define them. I now actually grab my FF and DFF and put them here. And I call this function with the starting point 1, FF, and DFF. And that's it. Okay? But now that I want to go to a different problem, all I need to quickly change is this part of the code and just say Newton method. I already have a function. So can everybody make this part work? Again, grab the code that did Newton method, define it as a new function, and that function will have the starting point, function, and derivative as input. And if you think about it a little more deeply, it's really cool of Python to treat these to be whatever they are. They could be variables, they could be name of functions, they could be scalars, they could be NP arrays, they could be text, that can be anything. So that's pretty darn flexible. Because coming in, I have no clue what they are, right? And then again, this is my function that I had in my previous, and this is how I call this function. Now, if I wanted to do a little something different, so just in a different cell, I'm not very inventive with names here, and I wasn't inventive with the function either. I just removed one of the terms there just to create a slightly different something. So it's not x to the 4 minus x minus 10, it's I removed minus x, okay? And I corrected my derivative as well, and now I just call it this way. So any now change of the function, you just define function and the derivative. For some other method, it might not be, derivative might not be needed. Newton's method is the only one that uses it. Okay? So this is just making the code a little more reusable, okay? Or reusable in a more elegant manner. Yeah? Now, if you were really cool, then you would compose all of the methods that you have, okay, and create a Python code, strict Python code, and then you just import that code, right? So if I define all of the methods as Python code and I call them rootFinding.py, then to use them elsewhere, I just have to have that code in my directory, and then I just say import root finding, and all the methods are available. There's that little, at the end of the programming lesson, I had the how to do that. Okay. And then they're all simply available in that code. You have them coded up, because the mechanics of all of the methods is the same. What you're changing is your starting point, x0 in this method, and in bisection or false position methods, you're changing the bracket, x lower and x upper part. Right? And you can change the number of iterations and so forth as you please. So that can be input to the function as well. Any of these parameters could be input. You can design it the way you want it, okay? And then create a Python script that will basically have all of those functions within. And the moment you need to use them, you just define yourself a function f and you go. Okay. Does any of this make sense? Class is awfully silent. Okay.
Question.
Yes. Thank you.
Yeah, to make To import something like when you say that you have to have a root directory, you mean just have like a regular file like that saved.
Yes.
And you can just put import. Right here would be Lecture5. What would you import?
Well, this is yes. So great question. So this is actually a notebook. So this is Jupyter Notebook. So you can't import that. It has to be exported as a Python code. But I could save this as download as, and then one of the options should be Python. Okay, and then it's gonna strip away all of the comments or any kind of special cells and just have Python code. And then you can import it. So it has to be .py.
Oh, that's that easy.
Yeah.
You just call it by that?
Yeah, you can call it whatever you... This would be a little... Not the best way to call it, but yes, you can. You can call it anything you want. Okay? And I have at the end of lecture 3, there was a, if you remember. So any kind of functions, and then you can... Now, what we typically say is we say import numpy as np, and then we carry that np dot, okay? You don't have to do that necessarily. You can just say import numpy, and then you don't have. But it is good to mentally distinguish that this belongs to numpy versus some other, because you could be importing multiple other methods. And for instance, sine function or this Newton method could be one done by you, and there could be one, there's one in SciPy, okay? So there's an optimization session there where you could actually import something that has been programmed by somebody else. So in order to have those multiples, you carry the naming. Okay? So you don't have to carry the naming. So you could just say this is root finding, okay? And then you just say import root finding, and then you just use Newton method, or however you call the methods. So that's okay? All right. And then you can also share it with people. So that's the code that you can share with others and say just import to use.
How would you share it? Just
email it to somebody. Yeah. Yeah. You send me yours, I put it here, and so that's how NumPy is shared, okay? Now, your numpy.py does not sit in your directory. It sits on what's called a path. So it doesn't have to be the current directory. I'm just not going into details. It could be anywhere else where Python can find it, and you can tell Python how to find it. Okay? That's how all of the programs actually work. They're in their own directories, somewhere in applications directory that you have on your computer, or programs, or whatever is the standard way to put it. Right? And then you have something called path that knows where all of these executables that start individual programs are, or any other parts of the program that are needed at runtime, what's called the runtime. Okay. So there's something called path in the computer that you can add. You can define any directory you'd like where you keep your stuff, and you add it to the path, and then computer will know where to find it. And what computer does is just like really anything that gets executed, all computer does is goes to all of the known folders on that path and searches for executable under that name. And if it cannot find it, then there's trouble. Okay? So basically, whenever you install program, you're really just moving all of those files to known locations that computer can then use. Because it's been already typically pre-compiled, and it just kind of gets on your computer. Yeah? Okay. So again, that's the software engineering and how it's done in a nutshell. All right. So we are ready for a new lesson. Very good timing. You walked in just into the right time. So we're going to start lecture 6, which is on linear systems. And I have a worksheet that we're going to start with. So I'm going to take a piece of paper, and just yes. So just take some just set up
Is that too shit?
Oh, did I give you my first copy? got 2 sheets. That's my original, sorry. That I made a copy for. So just a quick introduction. Does everybody have a copy? So quick introduction before we start working on it. So linear systems, solving linear systems of equation is a huge topic, okay, in numerical methods, and is one of the most important ones. So we have completed our first topic in numerical methods. Before that, it was really just programming. Okay? And we did root finding. We covered both what's called bracketing methods, bisection and false position, as well as open methods, which are fixed point, Newton-Raphson, secant, and modified secant. And today we're actually starting systems of linear equations. Now, just to kind of quick introduction, this is something you have probably seen in high school sometime. Yes? No? Yes. And how many of you are in ordinary differential equations? And how many of you have completed ordinary differential? So there was linear algebra part, and solving linear systems was part of that course, am I correct? Whether you remember it or not? Okay. Well, so the simple one here, and that's what we're going to review today, you can find multiple ways to solve this one. One way to be that kind of jumps at you here is to just sum up these 2 equations. Okay, and when you sum them up, you will eliminate y, okay, and that will enable you to compute x, so 2x is 6, x is 3, and then y has to be 1, whether you put it in the first one or the second one, okay? Now, you can actually get funny. This was floating at some point on my Facebook. Granted, I have a few mathematician friends. So, this is x is life, y is love. And then you can solve for life. Okay? So real life is half happy and half sad. Some people are laughing, some people are like, really, Dr. Pradarish, really? Well, that's the reality. Anyway, so real engineering stuff, okay? This is what floats on Facebook, and this is what engineers have to deal with, okay? We'll have multiple things to solve for. So 2 by 2 system that we did in high school, or a 3 by 3 maybe, doesn't apply, doesn't cut it. Even though most of the time as we're learning the mechanics of how to do it, we're going to indeed do 2 by 2 and 3 by 3 systems. In reality, you have n equations and n unknowns, and in reservoir engineering, that n is typically on the order of 1 million. Okay? And you would, of course, the moment you can solve for 1 million, you want to solve for more. So, 1 million equations at the same time, so that is not a laughable matter to solve efficiently. And you never want to solve it once, you want to solve it multiple times, right? Because in reservoir engineering, you want to go through multiple scenarios, right, on how to optimize a field, and you can't do that by just running one simulation. So normally, the whole reason to actually invoke linear algebra in this class was that the way we represent these systems is as a matrix of coefficients. So I take these elements, A11, A12, A1n, all the way, and these coefficients become coefficients in a matrix, A. Okay? And then if I actually look at it, my matrix multiplication here applies. If I take a matrix that is defined with A11, A12, all the way to A1n, and I proceed and take row by row, my first row okay, on the left-hand side, it's actually multiplication of matrix A and vector X. X1, X2, all the way to Xn. Does everybody see that? So you can convince yourself with a very small system on a piece of paper. That's the way to go when you don't necessarily immediately see. But this first row is basically this matrix, first row, the matrix A, and dot product with vector X, okay? Which is precisely how I do matrix multiplication. And then on the right-hand side, I have a coefficient B. So A and B are I know. And as a general rule, in order to solve this system, and if I have n equations, I have to have n. If I have n unknowns, I have to have n equations at the minimum to solve. Now, not only that, those equations should be also well put together, and we're going to get to that in a moment. So this is one example where you wouldn't think about it. But actually, if you solve, so this is finite element analysis of well-bore strengthening. So this is half of a well-bore. And whenever I'm in a well-bore situation, I have cut out a cylinder, okay, of rock. That cylinder is now missing. Okay? However, my forcing on that cylinder is still the same, and earth stresses are acting to basically close it down. And the worst part of it is that earth stresses are always uneven. I never really have an isotropic situation where all of the stressing is the same. Because of that, okay, it's like if somebody is actually putting your curved system, you have just like sort of like your neck. And if you curve yourself like this, and somebody is acting on you, this portion will hurt the most, correct? Somebody compresses you, it's kind of going to pinch. There will be this curved portion of your neck will be a pinching point. Well, pretty much that's what happens in the well-bore as well. If I actually have a larger horizontal, this is a horizontal cross-section. If I have a larger horizontal stress from one side and smaller from the other side, then there will be a concentration of stresses right here. Just imagine that this is your neck and this is your sort of your curved shoulders of sorts, and somebody is squeezing you much more from one side than the other. The neck will hurt the most, okay? That's where I actually have a concentration of stress, and it could be even 4 times the difference between these two. Okay? And also here, not only that there is no, so here I might have extra stress, and here I might actually go into tension. Especially if I'm helping it with the fluid from the well-bore that is acting to reduce the stresses. So if I go into tension, I actually might split the rock open, and this is precisely what hydraulic fracturing is doing. Okay? Now to analyze what stresses, and as my fracture here propagates, I actually have a concentration of stress here just ahead of the fracture tip because the rock is splitting open, okay, to relieve that stress. So essentially, to get this stress field everywhere around the well-bore, I actually have to solve at each of these elements that you see this, I have to solve linear equations. My problem of finding stresses comes down to actually solving linear systems, as it does for most of the differential equations that are solved on a larger limit. So we don't necessarily think about that, but all of every time you kind of see a physical problem solved, like this one, okay, actually what's underneath, the numerical method underneath has to solve multiple linear systems at each of these discretized elements that are part of the domain. Okay. So this is why it's very important to study linear systems. So for instance, this resolving stresses and getting this beautiful colorful plot that tells me where I have stress concentrations, where I have possible splitting things open, okay? That comes from solving linear systems ultimately. Somebody has set up a numerical method and one can actually solve it. Okay. So in general, I have AX equals to B, so I hope that the it's going to get a little dry because it will constantly just work with ax is equal to b, but always remember that there is actually a real physical reason why we want to solve these, okay? So it's not always as dry. So normally I need n equations to solve unknowns. If I have more equations than I need, it's called overdetermined system. And if I have less than I need, it's underdetermined, and this is actually part of optimization, so we're not going to go into that, okay? So just to actually point that, if I have two equations, one of them x plus 1, y is equal to 1, and the other one is 2x plus 2y is equal to 2, do I actually have a properly determined system? I do. Can I solve for both x and y?
Yes.
Okay, what is x, what is y?
X is 1 minus y. Then you take 1 minus y, plug it into the second equation.
And
so
what do you get?
It's going to be 2 times 1 minus y. So it's going to be 2 minus 2y plus 2y, which is going to be 2 equals 2.
Yeah. So is that does that equation give me any new information? 2 equals to 2. No. So basically what happens here, it appears I have two equations, but they're so-called linearly dependent. This one is just 2 times the first one. So it doesn't give me new constraint. Okay? Therefore, the only one I have is x plus y is equal to 1, so it's actually underdetermined systems. So that's something that we need to be careful for. So I don't have, well, I have a solution. It's just not unique. Solution is this entire line. This defines a line. So that gives me a great introduction to our worksheet. So let's actually walk through some of these examples. So open up page 1. And I'm going to open it up here on a computer as well, just in case if you want to take a look. So I would like you to work on it. And let's try to finish a good portion of it today. Okay. So in first one, with whichever method you already know and love, please solve this system of 2 equations and 2 unknowns. And if you're done with that, then I would like you to sketch the solution geometrically. Okay, so draw an x1, x2 coordinate system. What do I need to draw a line? 2 points. So find 2 points that are sitting on those lines. Plug in whatever values you'd like. And find 2 points and then draw that line. And the same for both. And then find the intersection of those 2 lines. That's the geometrical solution to the problem. And if you're done with drawing, then you can think about B and C. What did I come up with? So the solution at the intersection of two lines is a point. That is the intersection of two lines. Now if I try to generalize that in 3 dimensions, if I say something like x1 plus x2 plus x3 is equal to 7, that defines what? In 3 dimensions. Plane. So if I was intersecting 2 planes, I would get O line, only to define a line. And then I need a 3rd plane to get intersection. So to get a point in 3 dimensions, so that's my 3 by 3 system is needed to define the solution. Let's geometrically visualize it. Why do I need n equation for n unknown? Now, what happens if you have two planes that are parallel? They don't intersect. That means not. I could also have, when I have the case of it looks like and I multiply it by 2. All I'm doing, I'm not defining anything, it's just collapsing. So that means that the entire plane, entire line. So that kind of visualizes situations where I have unique solution, where I have infinite number of solutions, so if my entire line is a solution, that's mine. Or if I can run solution at all, then parallel lines are parallel. And that's again because we formulate engineering problems with these equations, and some problems don't have or if I know that too many equations are good. No matter what happens, give it a, and that's actually traffic flow. You don't want the precisely one solution. Precisely one speed.
No, wait.
That is, try reinstalling. That's might be that your Firefox or whatever is outdated and is it maybe just taking a long time? Do you have anything else running? Yeah, maybe there was an update to the browser. Okay. All right. So, has everybody drawn these solutions? Needless to say, this is going to be your quiz grade, submitting this piece of paper. So, has everybody plotted it? Yeah, it's intersection. So, geometrically, when I'm looking at these, it's an intersection of 2 lines. So, it's a point that is an intersection of 2 lines. Okay. Now, what happens if I actually did that in multiple dimensions? Okay. So if I have something like x1 plus x2 plus x3 is equal to 7, that is a definition of a plane. Okay. So plane is something like that. Okay. Now, in order to get a unique solution, if I get another plane, the intersection of 2 planes is a line in 3D. And then I need another 3rd plane to come in, okay, to actually get me a point that is at the intersection of three planes. Okay. So in 3 dimensions, if I was looking for a 3-dimensional solution, x1, x2, x3, I would have to have 3 equations to define a unique solution. Now, that's all great when I have a unique solution. Who says that I posed my problem? Because ultimately this x plus y is equal to 1. That's really an engineer came up with those equations and they mean x and y means something. So what happens if I have a situation like here in 3? This first system, does it have a solution? So the second equation is simply the first one multiplied by -1. So in itself, it doesn't bring me any new constraints. So all I have is this first equation. So yes, I have a solution, and it's that entire line. It's infinitely many points on a line. That's not necessarily a bad thing. Okay? So if you think about it, flow of traffic in a city is technically a solution to a linear system, okay, for the individual fluxes of cars per each street. It'd be a really bad situation if I only had one solution. That means that drivers would have to hit precisely the correct speed, or otherwise I wouldn't be moving in a city. That's not good. Okay? So in most situations like that, where I have networks with multiply connected streets and so forth, I'm going to have multiple solutions at multiple different fluxes of cars, or I might have water system and pipes, right? So that's a good thing. Having infinite number of solutions is actually, in practical sense, a very good thing. Okay? However, the second part is not a good thing. So what's happening here? 7 is not equal to 5, so I don't have a solution. What does it mean geometrically? Where is this line? So I have this first one, okay? Where is 3x1 plus x2 is equals to 5? Where is it with respect to the lines that you drew? Parallel. Okay? So I have 2 lines that are parallel to each other. They never intersect. Therefore, there is no solution. Same in 3D. If I had parallel planes that never intersect, I would have no solution. So you can actually draw this line. Okay, you can draw this line and see where it's at. Okay.
Are A and B two separate things?
Are what?
Like does A have a solution and B doesn't?
So this one has infinitely many solutions. So it has a solution. It has many more. Okay. And this one doesn't have a solution at all.
Did you say A?
Well, yes, they're separate questions. Okay, do the following systems have solutions? There we go. That same question applies to A and B. That's the way I was thinking. But hey, this works. Improved grammar for better understanding. They're parallel, lines that are parallel, and therefore they don't intersect and have no solutions. And that's the graphical explanation. All right.
Do you want us to graph it?
If you would like insight, do it for yourself. Now let's look at this. How can I represent this system? The next question is asking, how can I represent this system as a matrix of some constant coefficients multiplying my unknowns x1 and x2? So this is matrix times a vector, and this vector is vector of unknowns. So what is my, if I want to present it as AX is equal to B, what is my A, what is my X, what is my B?
Is 3, 1 minus 3.
So my A has coefficients 3, 1, minus 3, and 2. Okay? So this is A11, A12, or A00 if you'd like it in Python. Okay? So this is my first row is 3, 1, the second row minus 3, 2. And that's multiplying a vector x1, x2, right? So this really, if you need to multiply, multiply on paper so that you understand that. Okay? So do that. Multiply 3, 1, minus 3, and 2 with the x1, x2. What do you get?
You mean x1 is 2 and x2 is 1?
No, just in general. 3x1 plus x2. Yes. Minus 3x1 plus 2x2. That's what you get. And that's precisely what your equations are on the left-hand side. This looks simple for 2 by 2, but is key for algorithms that solve this. Okay? I want to go and program, and when I program, I want to program for any size matrix A, so I just fire it up and say solve. Okay? Because 2 by 2s, 3 by 3s, I can do by hand all day long, not a problem. 4 by 4, that's already, it's not something I would give on an exam. That exam wouldn't finish on time. Okay? So it can pile up. And if I need million by a million, I ain't doing that by hand anytime soon. Okay? In 1950s, we had human computers as a job. Well, those human computers were not solving systems of that size, and never will. Okay? But if I can actually formulate any of these problems as A, x is equal to b, and then program in a general way to just go for any size matrix A, I'm cooking. Okay? And that's why linear algebra is actually so important. For you, it looks like something, oh, why is somebody torturing me with this, right? It is very, very practical importance. For a plane to rise up, okay? At every click, we are solving systems like this just to be able to get off, okay? So being able to just execute on a click is very important. Okay? And it's key to basically getting to solutions of systems that really matter in engineering. So just for kicks, define this matrix A and vector B in Python. And this has obviously already been solved. We're going to go through mechanics of it ourselves and programming how to program, okay? But there's already np.linalg.solve that as long as you define A and B, you can already solve the system, okay? So we're going to continue with this on Wednesday. Not now, so I'll do it on Wednesday, okay?